So, yesterday we are discussing Hermitian matrices, and then we discussed what is called autocovariance matrix, autocorrelation matrix and all that. So, let us start from there. Briefly, to recall what is an Hermitian transposition, that is conjugate transposition. For say real matrices or real vectors, it is simple transposition, but for complex value matrices, it is conjugate transposition. Okay. And then if a matrix, and matrix is a vector is a special case of matrix. Matrix is m cross n, any 1 cross n matrix is a vector. So, I may talk in terms of matrix, but that includes vectors also. Okay. Any matrix A, if AH is A, then A is called Hermitian. Okay. A Hermitian. So, you understand, for this to be true, matrix has to be square. A Hermitian means you are taking transpose. Transpose and original matrix, if they are same, means dimensionally they have to match. That means number of row and number of column of A have to be same, which means the square matrix. That goes without saying. Then we discussed that, okay, we said that, look, suppose we consider a vector x, random vector, means it consists of say p number of random variables. Any vector or scalar indicated by me by an underscore. Normally uppercase letters with underscore, lowercase letters with underscore for vector, uppercase letters with underscore as matrices. Sometimes, by mistake I might skip. I might just, you either tell me or you assume as it is. Okay. Because always I may not be able to stick to this underscoring thing. Sometimes I may just skip unwittingly. Okay. And then the mean of this is, there is a mean vector E of x. E of x means a vector like this, where you have got E of x1 dot dot dot, say E of xp. We can even write it as say mu 1. Yesterday I called mu x1. Yesterday I called mu x1. Let me call it mu 1 because there is no other thing, mu p. Okay. And then I said that if you subtract, if you consider this vector say x tilde as x minus mu x vector, it will give only the deviation across the mean. And then if you take this E of x tilde Hermitian, I called it autocovariance matrix C. You can even indicate Cp cross P to indicate the matrix. And what does this matrix give? Today I will not expand, yesterday I expanded. Just for your consumption, you remember one thing. Suppose I give you a vector, forget about all this. Suppose I give you a vector, say u as u1 dot 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 up, and I give another vector same length v, v1 dot 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 vp, and if you multiply u with v Hermitian, what do you get? Column vector u, v Hermitian means it becomes row vector with conjugate. If you take this matrix and its general element, ijth element, what will that be? See how the matrix is formed. u1 into v1 star, first element, u1 into v2 star, u1 dot 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 vp star, that is the first row. Ith row means uy into v1 star, uy into v2 star. So, jth element means uy into vj star, uy here, ith element from here, jth element from here. This is okay. So, what is general element, ijth element? Of course, I and j remaining within 1 to p. This is simply ith element of here, jth element of a conjugate with expectation, isn't it? So, that means x, what is x tilde vector? Xi, I mean, if it is a component xi minus mu y, that is the ith component here of this vector, and jth component of that x tilde minus mu x tilde j minus mu j star. Okay. Pardon me? Sorry, no tilde. I am sorry. Xj minus mu j. Sorry, xj minus mu j star. That is coming from the tilde vector. Xj minus mu j star. So, obviously, this is the covariance between xi and xj. Okay. If this is 0, then xi and xj are uncorrelated, all those things you have seen, that I am coming separately. That this matrix we have seen yesterday is Hermitian. That you can see directly, I told you yesterday, but I repeat again here. You can see CPPij is this. What is C? I am just showing various ways because we will be doing this kind of exercise too often, so I am just making you familiar. What is the jith element? E of this will come first, xj minus mu j, and so obviously this is conjugate of this. So ijth element and jith, they are same but conjugate of each other. So it is conjugate symmetric. This way you can say it is Hermitian. Even otherwise you say, as I told yesterday, you don't have to do all this by simply algebra. If you take Hermitian of this matrix, Hermitian operation, you take Hermitian of this, you can push Hermitian operation inside expectation operation. Because expectation means what? Any term is multiplied by some appropriate probability density integrated. So that will be replaced from ijth to jith, it will go. So you better move it first and then take expectation, rather than taking expectation first then move. And also a conjugation, but conjugation after multiplying by the probability and integrating is same as, you better first conjugate the variable and then integrate multiplying by px, because probability is a real function. So that way these are the mathematical things, you know, inside. So you can push Hermitian operation inside the E operation. If you do that, if you take this product x Hermitian, x tilde Hermitian of that, first second term will come first, Hermitian and Hermitian will cancel, so you get back x tilde, and first term will go second with Hermitian, x tilde Hermitian, which get back the same thing. That proves that is Hermitian. Okay. And if mu x, if you take only this vector, this much, only x, no subtraction of mu, no subtraction of mu, then it is called correlation matrix or matrix P cross P, correlation matrix. This to become same, this also Hermitian you can easily see by the structures here, expectation of something into something transfer, Hermitian, isn't it? And this becomes same as this when your mu x is 0. For 0 mean processes, 0 mean random variables, correlation and covariance are same. Okay. As a special case now, consider this, that suppose there is a discrete time random process xn. So xn minus 1, xn minus 2, that is so this is given. Stationary or not, I am not speaking so far. I am just taking some samples. Please note all these things carefully, because later in the analysis of adaptive filter, I will make use of all these results frequently. So I will not repeat, re-derive this. So actually p plus 1 elements I have taken, n minus 0, n minus 1 up to n minus p. So it is not p plus 1. Suppose I form a vector like this, I will call it x. I can, if I take this Ex and x Hermitian, this will be a correlation matrix. Okay. And if mean of these samples is 0, then there will be covariance matrix also. What it will look like? Now I write in an expanded form. First one will be mod xn square, isn't it? Xn into xn. Then will be, this is a very important matrix. So that is why I am doing this way, xn into x star n minus 1 dot 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 e xn x star n minus p. Next row will be x what? You can see it is a conjugate of this. Even otherwise you can take a, because of the Hermitian property, this conjugate will come here, na? dot 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 okay. So far there is nothing special, this is just a correlation matrix. You only in this earlier it was giving general variables x1, x2, now specific terms xn, xn minus 1, xn minus 2, so on and so forth. So in terms of those or rather in terms of the corresponding correlation, this matrix elements will be obtained. That's all. That's the only thing. But now suppose, and this is always Hermitian. Now suppose I say this xn also is White-Sense stationary. That means correlation is dependent only on the gap. So then it takes a very interesting structure. Firstly, you see, even if not stationary, this matrix, if I know one half, diagonal and the upper half, lower half can be constructed because of the Hermitian property, conjugate transpose, isn't it? One half is enough for me, upper triangular part with the diagonal and lower triangular part with the diagonal. Now you see, if it is stationary, if WSS, this leads to what? And I write separately here, I define E of xn x star n minus k correlation, it is equal to R, I should write Rxx, but for the time being I am dropping xx because I am handling only one random process, so no point in writing too much. So you can easily understand what I am referring to. So this is Rk, this is the definition. With this definition in mind, what is the matrix? First one will be R0, which is expected instantaneous power R0. Then will be, please see this, what is this? R1, then R2, dot 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 Rp, and obviously this will be R star 1, Hermitian property. Then again R0, then again I have not shown it here, what will be the next one? R1, then R2, dot 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 Rp minus 1. You will see along this diagonal R0 will propagate because of stationarity, whether it is E of mod xn square or E of mod xn minus 1 square or E of mod R0, isn't it? Similarly, along this subdiagonal R1 will propagate, along this subdiagonal R2 will propagate, so on and so forth. And on this side, whatever is the element, that also will propagate. This kind of matrices are called Toeplitz matrix. This is a special case. This is this Hermitian Toeplitz. In the case of Toeplitz, this may not be R star 1, it could be anybody, A. So A. This next one could be B. That is the general Toeplitz matrix. But this is not only Toeplitz, this has got another structure, Hermitian, that this element and this element are conjugate of each other. This guy and this guy are conjugate of each other. There is an extra thing which is Hermitian property. So this is, I am writing Hermitian. This matrix plays a very key role in all signal processing applications, statistical signal processing, adaptive signal processing, linear prediction, that is filters, because we often handle stationary processes, or model the process to be stationary, then only we proceed further. Immediately the correlation matrix we get, that is a Toeplitz matrix. This matrix has beautiful properties that in a sense, if you know one row or one column, entire matrix is known, isn't it? You can construct. So that means this matrix has lot of redundancy, which means if you are solving an equation Ax equal to B and A is matrix of this kind, very fast algorithms can be developed because there is too much of redundancy in the matrix elements, and those algorithms exist. Very powerful algorithms which come in various contexts of signal processing involving stationary processes. This is a Hermitian Toeplitz matrix. This special case I have discussed. Again, I come back to general Hermitian matrices. General Hermitian matrices, of which correlation or covariance matrix are some examples. Okay. So suppose not H, suppose T a Hermitian matrix. T you can call P cross P. I am writing P cross P, but when I go to the adaptive filter part, it will all become P plus 1 into P plus 1, like it became last time. Simply because last time if I had taken, I had taken from xn to xn minus p, if I wanted to make it length p and not p plus 1, I would have had to put n minus p plus 1. So again, everywhere, n minus p plus 1, writing too much. So I better make it p plus 1 and go up to n minus p, just for my writing, convenience in writing, nothing else. Huh? Suppose it's a Hermitian matrix in general. P cross P Hermitian matrix, complex valued in general. Hermitian means it implies T Hermitian is T. I am skipping this underscore often, please excuse me. Then first consider this eigenvalue eigenvector problem. So suppose there is you are solving this equation. You know eigenvector eigenvalue problem, na? That firstly this vector x must be non-zero. This equation is valid for any zero vector, so you cannot find out a lambda. Eigenvectors are by the definition non-zero vectors. And you are solving an equation like this. What is the meaning of eigenvector? Is such a vector that when you multiply by t, you don't get any arbitrary vector, you get back the same guy, just scaled up or down by an element called lambda. That is in a geometrical sense, it was pointing in direction. After you operate it, there are many operations of vector, rotation, translation, but it is such an operation that when you operate on that particular vector, not for any vector, on that particular vector, there is given an operation, it has got some specific vectors called eigenvectors. You are taking one eigenvector. If you operate that eigenvector using that operator, it will result in a vector pointing in the same direction. Its magnitude only will change by a factor lambda. Lambda could be complex in general. This is called eigenvector eigenvalue problem, and x cannot be 0. Okay. Suppose T is Hermitian. Now let us derive some interesting property and very simple properties, very simply derived. Suppose I take Hermitian of both sides. I can do that. So if I take Hermitian of left hand side, what will I get? X Hermitian, T Hermitian, and T Hermitian is T, because T is a Hermitian matrix. So that means X Hermitian T, and Hermitian of right hand side means lambda star. You will take conjugate, every element is multiplied by lambda. You will take conjugate and transpose, lambda will be replaced by lambda star. Then again pull out lambda star. So it will become lambda star xh. So x Hermitian is a row vector multiplied by a matrix. So reality will be a row vector. The row vector, if I now multiply here, this is a row vector. If I now bring back x here, then row into column, it will be a scalar, isn't it? And lambda star, but Tx is lambda x. See, this matrix multiplication is commutative or associative. It's okay. You are multiplying this with this and then result with this. You can also do this with this followed by this with this, isn't it? But Tx is lambda x. So bring back lambda x here. Lambda is a scalar, take it out. So you get back lambda x Hermitian x. Okay, on this side lambda star x Hermitian x. So now this result in this thing, lambda minus lambda star equal to 0. Isn't it? I am not showing you intermediate steps, they are very silly, very simple steps. Now x is a non-zero vector. What is x Hermitian x? Like, I mean, if x is of this kind, x1 dot 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 xp, what is x Hermitian x? Summation mod xi square I from 1 to p. This is always real, non-negative. If it is 0, every term has to be 0, because every term is a mod square term, isn't it? If the entire summation has to be 0, every term has to be 0. And every term has to be 0 means each xi is 0, which means x is a 0 vector, but that is ruled out, because x is an eigenvector, x cannot be 0 vector. So, that means this is always greater than 0. So, in this equation then this is equal to 0, this implies, because this cannot be 0. Okay. This implies lambda equal to lambda star, which means lambda is a real value. So, even if matrix is Hermitian and complex valued Hermitian matrix, eigenvectors are in general complex values, eigenvalues are all real of a Hermitian matrix. So, for any correlation matrix, if we find out eigenvalues, they are all real. Okay. Another property, suppose I have got two distinct eigenvalues, T x 1 as say lambda 1 x 1, T x 2 lambda 2 x 2, and lambda 1 and lambda 2 they are not same, two distinct eigenvalues. Then I can do one thing on this matrix, just a minute. You take the Hermitian of both sides of the first equation. So, you get x 1 Hermitian, T Hermitian which is T, and on this side lambda 1 star x 1 h, but I have proved lambda is real. So, that means this is equal to simply lambda 1. This is the reason why I have to prove that. Okay. This now on this side I multiply by x 2. So, here also I multiply by x 2, here also. Okay. Now, T x 2 is from the second equation lambda 2 x 2. So, take that out. So, this will lead to this lambda 2 minus lambda 1 but I told you I am taking distinct eigenvalues, lambda 1 and lambda 2 are not same. So, this cannot be 0, that means this is equal to 0. So, if this is 0, that means we say they are orthogonal. Two vectors in our definition, if they satisfy this kind of thing, two vectors x and y. If you do the x Hermitian y, okay, or y Hermitian x Hermitian y, that means 0, that will mean y Hermitian x also 0. Okay, you have to take Hermitian of both sides there. Then x and y are called orthogonal. Actually, you have done dot product of vectors in the three-dimensional world. So, p vector and q vector, p dot q, p suppose was p1, p2, p3. Q was say Q1, Q2, Q3. What is P dot Q? P1, Q1 plus Q, P2, Q2 plus, that is P transpose, this is P1, P2, P3, transpose of this into Q1, Q2, Q3, isn't it? That was the dot product. But if they are complex valued, you can generalize. This is a generalized definition of a dot product, where they are not only transpose, they are conjugate transpose. And then take this, that is the dot product between two vectors P and Q in a general algebraic sense, not in the three-dimensional world, because there is nothing complex there. Okay, and you can generalize from 3 dimension to any dimension. So, there is so giving two vectors x and y, x Hermitian y is a dot product. A dot product there is called inner product. This is a more general term than dot product. Inner product. I will discuss all this later at length when I come to vector space theory. This dot product, and dot product 0 means orthogonal. Like P and Q, if the dot product is 0, that's orthogonal. But there is a geometric sense there directly. You can see visual geometric sense. I would say geometry is there everywhere. But there is a visual geometric sense. You can see the angle is 90 degree and all those things. Okay. So, x1 Hermitian, x2 0. Now, suppose to start with, T is such a matrix, P cross Q matrix. How many eigenvalues it can have at the most? P eigenvalues. P cross P matrix, you solve the characteristic equation, you can have at the most P roots. And for the time being, assume that all the P roots are distinct. When not distinct, what happens? I will just tell a few lines, I will not prove, but that is heart of the linear algebra thing. You have to just take down take down what I say. But just to start with, assume all the P roots are distinct. So, I have got lambda 1 up to lambda p all real, and I have got these equations T E k as lambda k E k. Lambda k is the kth eigenvalue given lambda 1 not equal to lambda 2 distinct, not equal to dot dot dot, not equal to lambda p. This is the case I am handling first. Okay. So, in that case, can I write here directly? Suppose I just put the eigenvector side by side, E p. What will this be? T into E 1 will be the first column, T into E 2 will be the second column, so on and so forth, and T E 1 is lambda 1 E 1, lambda 2 E 2. These are all column vectors. These are all column vectors. Now, my claim is I can write it like this. The same vector if I bring in E 1, E 2 dot 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 E p into lambda 1, lambda 2 dot 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 lambda p, a diagonal matrix. This will give you this. No, can you see that? How do you do? When you do matrix into matrix multiplication, how do you do? Suppose A and B are two matrices. I come back to some rough work now for your benefit. I am trying to give you some extra things regarding basic matrix operations. Suppose you are given one matrix A, say element like A11, A12, A21, A22, another B. I am taking 2 by 2, from that you will see what I am trying to mean. B11, B12, B21, B21, B22. And you have to do A into B. How will you do? Normally, what do you do? Tell me. You do like this, A11 into B1 plus A1 into B22, one term, A11 into, like that, isn't it? So, from today's class, you should never do that. That is not the way you should do. That is done in the school level and all that level, not anymore now. My claim is, if you call this column is a column vector A1, first column, A2, then this will be matrix, again 2 column. First column will be this column vector times B11 scalar plus second column times B21 first series. If you take this column B11 times this, B11 into this, B11 into this, and take this column B21 into this, B21 into this, add, do you get back the same quantity? Can everybody see that? B11 times this column vector. So, first element A11, B11 stored, what is this? A21, B11 stored, and then this guy into second column, B21, A12 stored on top, B21, A22 stored, and you are adding. So, you get back this, isn't it? That thing A11 into B11 plus A1 into B22, B21. Are you convinced or not? Similarly, here you now combine with this B12 into again A1 plus B22 A2. There is even forget about matrix, if it is a vector only. For any column vector, matrix times column vector, what you are doing? You are taking the first element, multiplying the first column with that, second element, multiplying the second column with that, like that, and then adding. That will be the net thing. That is this matrix into that vector. Again, this matrix into this vector, do accordingly. So, that means you are linearly combining these column vectors by the elements of this column here, linear combination of these columns by the elements here. That will give you here, take you here. Again take the next fellow, linearly combine the columns, B1 2 times this column, B this times this column. If there are more columns, this into third, fourth into fourth, and then add. That will be the corresponding resulting column vector. Okay. Are you convinced? Now come to this. I had, please have a look. I had lambda 1 scalar times E1, lambda 2 scalar times E2 dot dot dot, and say I can write like this. Very simply, first this is a matrix, first column, second column, pth column, this is a matrix. That times say first column here. That will give rise to the first column of the resulting product matrix. That should turn out to be this. But that is obvious, lambda 1 times E1, other fellows are 0. So, they are left out, lambda 1 into E1 comes. Okay. See how easily comes if you know that. Then here you have 0, so 0 into E1, forget it, other zeros forget, only E2 picked up by lambda 2. That comes here, so on and so forth. All the eigenvalues are real. You give a name to this matrix D, diagonal matrix D. You give a name to this matrix, say E. And this matrix E. So, that means I can write T E is E D. What are these columns? They are the eigenvectors corresponding to distinct eigenvalues. Isn't it? Distinct eigenvalues. This is for lambda 1, this is for lambda 2. That is how these vectors are obtained. And you do T into this, you get this. So, they are mutually orthogonal. E1 Hermitian, E2 0, E1 Hermitian, E3 0. Only Hermitian with itself will not be 0, because the vector is not 0, I told you. So, Hermitian with itself will be that summation of mod square terms which cannot be 0, because then every term has to be 0, which is a contradiction. So, all cross terms will be 0. So, if I say, if you take E matrix, if you take E Hermitian into E, if you take E Hermitian, what will happen? You have to take conjugate transpose of this matrix. The first column will become first row, transposition, and then conjugate of that, isn't it? So, here you will have E1 Hermitian, this guy becoming row, you take this first column, that will become row and every element conjugated. So, what is that actually? That row is nothing but original E1 Hermitian of that, then E2 Hermitian of that, dot dot dot, EP Hermitian of that. That is for EH, and E is E1, E2 as before, EP, Now, if you do the product, row vector, column vector, row vector, column vector. So, what do you see here? So, it will be a diagonal matrix, isn't it? E1 Hermitian with E1 only non-zero, E1 Hermitian with E2 to EP 0. Similarly, E2 Hermitian with E1 0, with E2 non-zero, but others 0. So, it will be a diagonal matrix. Acha. Here I forgot to do one thing, so I come back. When I was solving these equations, you know, T E equal to lambda E, this kind of equation, you got lambda 1 up to lambda P and E1 to EP. Whenever you get a vector, say E k Hermitian with E k, it is dot product with itself. It is called actually in our term norm square. In your vector algebra term, it is the square of the length of that vector, the norm square. This always positive have shown, because none of them is a 0 vector. Okay. So, if you call this quantity as norm square, it's a scalar term, you give it a name, say theta, theta k. Then instead of E k, if I take E k by square root, positive square root of theta k, if I take a vector like this also is an eigenvector with eigenvalue lambda. T of this, isn't it? There is a dividing, multiplying both sides by 1 by square root theta k, here also, and that you can pull inside below E, here also below E. So, this you can call a new vector, say E k prime. I am saying T E k prime also lambda E k prime, firstly. You must know if Ax equal to lambda x, x is an eigenvector, then 2x, 3x, 4x, all are eigenvectors of the same eigenvalue, scalar multiples. Okay. So, this, but what is the advantage of this E k prime? Is this, what is the norm square of E k prime? E k prime with, this is a scalar, and what kind of scalar? Positive real. So, you cannot conjugate it. E k Hermitian means when you take the Hermitian of it, this will become row vector with conjugate. So, this will get Hermitian transposed, but this will remain as it is, isn't it? Because this is real fellow. So, that will become, and from this E k prime, from E k prime also another square root theta k will come, isn't it? So, it will become theta k, square root will go, and then E k Hermitian E k, and E k Hermitian E k itself is theta k. So, theta k by theta k, which is equal to 1. So, this is called normalization. You can always find out the norm square of that, take the positive square root of that, divide the vector by that. That vector also is an eigenvector, but its norm square is unity. Okay. I forgot to mention that when I am dealing with this E1 to EP, I normalized each to have norm equal to 1. So, E1 Hermitian, E1 is 1, E2 Hermitian, E2 is 1, so on and so forth. So, in that case, this matrix becomes simply identity matrix. E1 Hermitian E1, others 0, E2 Hermitian E2, second diagonal entry, that is 1, others 0. Okay. So, it becomes 1 0 0 dot dot 0, 0 1 0 0 dot dot 0. Any matrix, and has to be a square matrix because otherwise this product cannot take place. Any matrix may not be Hermitian because E is not a Hermitian matrix. Here the E, that is not a Hermitian matrix. Any matrix, say E, if it satisfies a property that E Hermitian E is identity, then this matrix is called unitary matrix. And E Hermitian E is identity, that means E Hermitian is nothing but equivalent to E inverse. If I give a two square matrices A and B equal to I, you know B is A inverse and A is B inverse, that we know. So, that means to invert such a matrix, you really do not have to do enough computation, that inverting a matrix is a big problem. If the matrix is given to be unitary, you just take a Hermitian transposition, you immediately get its inverse. And therefore, this also implies that instead of EHE, if I make it EEH, that also is identity, because EH is inverse. Okay. So, that means TE is ED and E is unitary, T is unitary. Okay. Here I am writing the separate part. From this equation what I found, TE is equal to ED and E is unitary, D is a diagonal matrix of real diagonal values. So, if I now take this E square matrix, T square, E square, and bring another matrix here, EH, here also ED, EH, okay. But EEH cancels, I have told you unitary and EH is the inverse of E. So, that means T is This is the main result. T can be written in this kind of form, E, D, E, H, where E consists of the eigenvectors normalized to unity, D consists of the corresponding eigenvalues, and this is the Hermitian transposition of that. E consists of eigenvectors, and E is a unitary matrix here. E is a unitary matrix. Now, you can ask me that I assumed this thing, that lambda 1 to lambda p are distinct, and therefore E1, E2, EP, they are mutually orthogonal. But if lambda 1 to lambda p are not distinct, suppose lambda 1 and lambda 2 are same, isn't it? So, E1, E2, where from you get, and are they orthogonal because they correspond to the same eigenvalue, lambda 1 equal to lambda 2, isn't it? Then at least between these two I cannot have this kind of thing, that cross terms cancelling on linear product with itself even if one, so a diagonal matrix is formed, that kind of property won't hold good. There you have to just hear me out, that in such cases for Hermitian matrix T, your mother matrix is Hermitian matrix, I am finding out eigenvalue vectors and eigenvalues of a Hermitian matrix only. Okay. So, for Hermitian matrix, if suppose an eigenvalue is repeated, suppose E1, suppose lambda 1 equal to lambda 2 equal to say some lambda, then given this lambda you can find out two eigenvectors. If it is repeated twice, you can find out two eigenvectors which are mutually orthogonal, and that we put here. They will be orthogonal with the rest because their eigenvalues are distinct from this lambda and they are mutually orthogonal. So, this I will be able to prove now, because that will require a lot of things, there is a linear algebra course. Okay. Acha. So, remember, given a Hermitian matrix T, whose examples could be correlation or covariant matrix, not necessarily stationary. In the case of stationary, an extra structure comes up, Toeplitz. I am not taking any advantage of Toeplitz property, I am only taking Hermitian matrix. I even took a general Hermitian matrix. And that can be written as this is what we have proved. This kind of transformation E D, in fact E inverse in general, here because it is T Hermitian, E here Hermitian here, and the E Hermitian, E is a unitary matrix, so E Hermitian is the inverse of P, all those things, nice properties are there. But in general, if you have got structure like this, that you take one matrix, say A, then some diagonal matrix D, I am talking a very general case, I am giving extra input to you, A some matrix, not unitary, nothing, just A, into a diagonal matrix D into A inverse. A is invertible, that is the only thing I am assuming, A into D into A inverse, and you call the product as B. Then B and A, they are similarly related. I mean, this is called similarity transformation on B. In such cases, that is, suppose B is in general A D A inverse, whose special case is this, because A here is E, A inverse obviously E H, D is the diagonal matrix of eigenvalue, and T is stands for B. In this case, if you take determinant of this matrix B, what do you get? Determinant of a product is, you have to take determinant of the individual matrices, isn't it? So, determinant of A into determinant of D into determinant of A inverse. Now, determinant of A inverse, that is 1 by determinant of A. Do you know all this, or So, determinant of A and 1 by determinant of A, they will cancel. So, determinant of B will be simply product of, this determinant of D, and what is determinant of D is diagonal. So, simply product of the diagonal elements, in this case eigenvalues. So, determinant of a Hermitian matrix is just the product of the eigenvalues. So, if all eigenvalues are non-zero, then determinant is non-zero, it is invertible, because determinant is non-zero. On the other hand, if any eigenvalue happens to be 0, then that matrix B is not invertible. So, this is a product of, this is a product sign I equal to 1 to P Please understand, these are the core of statistical signal processing. We need this often, every now and then. I want you to be absolutely conversant with these properties, so that there is no scope of rethinking how this, how that, all that. And you will find this extremely useful in communication, control, signal processing, these three subjects. Lambda I. Okay. In this case, lambda is real and all that, so you will get a real product, fine. So it will be just product of the eigenvalue. That is one thing. Another thing, do you know this? That suppose A and B are two square matrices, two, say, M cross M matrices. You know the trace of a square matrix, what does it mean? Trace of a square matrix is summation of all the diagonal elements. Then do you know this trace of AB and trace of BA, they are same? You may not know, so just it's not difficult. What is trace of AB? If I find out the diagonal entries, what are the diagonal entries? AB is a product. What is the ith diagonal entry? Ith diagonal entry is AI, ith row of this guy. So Aij and Bji, j has to be moved from 1 to p. That is the ith AB product. I am talking about the AB product. I find the product matrix, what is the ijth entry. So that means ith row of A, jth column of B. Ith row of A means AI1, AI2, AI3 dot dot dot, and they are multiplied by jth column. Sorry. No, ith diagonal, na? I comma I. Sorry, I comma I. Yeah, I made a wrong statement. I am bothered about the diagonal element only. So the product matrix, not any arbitrary ij, I comma ith element. Sorry, I comma ith element. So that means I start with the ith row and ith column. Ith row of A, ith column of B. So I comma 1, 1 comma I comma 2, 2 comma I. Okay, and so that will be the I comma ith element, ith diagonal entry, and I have to sum all the diagonal entries. So then final summation over 1 to p. This you get on the left hand side. But I told you this is a finite sum, so you can interchange the double, and any DSP also, you know, the next step is, this is not DSP, but often double summation means you interchange the, if you interchange the two, the result comes immediately. Bji, I write like this, Aij. So jth row of B and jth column of A, they are multiplied and summed over all j. So this is this, okay. What does it imply here? Trace of, in general, A, D, A, again I am trying to give a more general case, A, D, A inverse, instead of here, instead of here. Whatever is true for this, that is true for this, do you agree? So that's why I am taking up this, though for us this is important, not that. So A into D is a square matrix. So you break it like this, trace of this into this is simply trace of A inverse into AD. Okay. Trace of this part into this part is same as trace of this goes first and this goes second. But you see A inverse and A will cancel. So simply trace of D. This result you don't forget, I make use of this result many times. So Hermitian matrix, its trace will be same, simply summation of the eigenvalues. So that means trace of T is summation of lambda i's. Please remember this, I will deal with trace of correlation matrix, autocorrelation matrix. At that time I will simply sum the eigenvalues. So don't ask a question then, get conversant with all this. Okay, now I come to a special kind of Hermitian matrices, that is called positive definite matrix. Have you heard of these terms, positive definite matrices? Maybe in stray way, I mean some communication course or some course, positive definite. image processing, fine. So, T positive, it can be positive definite or sometimes positive semi-definite. Positive semi-definite is also called non-negative definite. Positive definite or case is non-negative definite. Non-negative definite, definite, which is also called positive semi-definite. There are various ways people write, So, this case, this second half, this is a more general, I mean, I am concentrating on this, and whatever I say, I will just modify a little, so that will apply here. In either case, T first be a Hermitian. If not Hermitian, then we cannot do anything. If not Hermitian, then we cannot do anything. Okay. So, T first be Hermitian. T must be Hermitian. Secondly, so Hermitian we have already studied. So, there has to be something more. So, what is that? For, for this sign, for all x, where x is a non-zero vector. This is important. If you take this product x Hermitian Rx is some vector y, x Hermitian that thing, this must be real and greater than 0 if positive definite and greater than equal to 0 if non-negative definite. Positive definite or non-negative? Non-negative definite also called positive semi-definite. If this extra property holds, then it is called, our correlation matrices or covariance matrices, they are not only Hermitian, they are positive definite. Always non-negative definite, but we model them as, we can also take them as positive definite under some assumption which is in general valid. Okay. Sorry, this is T, I am very sorry, this is T. This is not R, this is T. I am so very sorry, because I started with T. I always have in mind correlation matrix R, so I am putting it here. X transpose Tx. In such case, before I wind up, 1 or 2 minutes, just one property you see, T is Hermitian, right? T is Hermitian. Now, again come to that eigenvalue problem. Suppose x is an eigenvalue, eigenvector of eigenvalue lambda for T. Lambda is real, we have seen, and x is a particular eigenvector, non-zero eigenvector, because x cannot be 0. X is an eigenvector, x cannot be 0, so x is a non-zero vector. So, here I told for all x, where x is non-zero. So, now I pick up x itself, multiply here, then I have to multiply this also by xh, but x is a non-zero vector. So, then this must be real, which is of course the case, because this becomes lambda into x Hermitian x, and x Hermitian x is always real. Okay. But if it is positive definite, suppose T is given to be positive definite or non-negative definite. Since it is Hermitian, by its definition, I took Tx equal to lambda x, lambda real, then I multiplied by xh, here also xh, x is a non-zero vector, which is an eigenvector. On the right hand side, I get lambda into x Hermitian x, but since it is also positive definite, this entire thing, since x is a non-zero vector, this product must be real. Real it is coming in any case, because this is real, eigenvalue is real, but this must also be greater than 0 or greater than equal to 0. Now, out of this is strictly greater than 0. This is norm square, strictly greater than 0. That means lambda, this implies lambda greater than 0 or lambda greater than equal to 0. So, if it is positive definite, eigenvalues are not only real, they are all positive. If it is positive semi-definite or non-negative definite, eigenvalues are not only real, they are non-negative. But non-negative means 0 can be included, which means matrix T may not be invertible, because the determinant, which is a product of the eigenvalue, some eigenvalue can still be 0. So, that is why we will often make as an assumption by which T will be your this thing, positive definite. So, I wind up today. So, this week we are not meeting anymore, because we have taken 3 classes. So, next time we meet, that is on Monday, 3:30. Okay. Thank you very much.